Let's talk about factoring today. Factoring is the process we use to rewrite an expression as the product of its factors. The common factor of each term in an expression that has the greatest coefficient and the greatest exponent is called the GCF. We know the GCF is normally referred to as the greatest common factor. Here's an example. The GCF for 4x cubed plus 20x squared minus 12x is going to be 4x. We have a perfect square trinomial. Those are important. A perfect square trinomial is anytime we have a trinomial that is the square of a binomial. For example, 25x squared minus 30x plus 9 can be factored as 5x minus 3 quantity squared. But an expression in the form of a squared minus b squared, that is not a perfect square trinomial. That's what is known as the difference of two squares. The difference of two squares. And that can be factored as conjugate pairs, a plus b times a minus b. 36x squared minus 25 is the difference of two squares. 36x squared is 6x times 6x, and 25 is 5 times 5. And notice what happens when you use distributive property. When you multiply 6x times negative 5 and 5 times 6x, those are additive inverses of each other, and that's why we don't have that middle term. And FOIL, that's a mnemonic for using the distributive property twice. You might have learned that in Algebra 1, first, outside, inside, and last. That way you make sure that you have covered all of the distributive property correctly. So let's look at factoring trinomials where the a value or the leading coefficient is either positive 1 or negative 1. So one approach, we want to figure out factors of 40 whose sum adds up to positive 14. So you could make a list of 1 times 40, 2 times 20, 4 times 10, and 5 times 8. So all of those are products whose answer is 40. But if you add 1 and 40, you don't get 14. 2 plus 20 does not give you 14, but 4 and 10, that's what we want. 4 plus 10 will add up to 14. So we would have factors of x plus 10 times x plus 4, because distributive property will give us 10 times 4 to get 40, and 4x and 10x will give us the 14. In part B, we're doing the same thing. We're looking for factors of 30, but the sum has to be negative 11. So that means we need two negative numbers. Negative 1 times negative 30 won't add up to negative 11. Negative 2 times negative 15 won't add up to negative 11. That gives us negative 17. Negative 3 times negative 10 would add up to negative 13, but negative 5 and negative 6 will multiply to give positive 30, and those two terms will add up to give us the negative 11 we need in the middle. So the two factors, our binomials, will be x minus 6 and x minus 5. Now remember, it doesn't matter whether you write the x minus 5 first and then the x minus 6 or the other way around. Either way is okay. And they'll both produce the same trinomial once you multiply. How about part C? We want factors of 21 that sum to give positive 4. So this is the guess and check method. We have 1 times 21 and 3 times 7. So 1 plus 21 is not what we want, but 3 plus 7 is not what we want. And this would be considered relatively prime. We can get factors that multiply to be 21, but they add up to be positive 10, and we had positive 4. Now this last one, you have negative x squared in front, so I'm going to write the trinomial in descending powers, and thinking of 1 times negative 36, or 2 times negative 18, or 3 times negative 12, and then 4 times negative 5. We're looking for a sum of 5. Well, 1 minus 36 is not 5. 2 minus 18 won't do it. 3 minus 12 won't do it. And 4 minus 9 will. Whoop, this should have been a 9, not a 5. We needed a 9. So how about if we take out the negative and rewrite this as x squared minus 5x minus 36. That way we could get negative 5 in the middle with 4 times 9, and our constant would be negative 36. So our factors are going to be x minus 9 and then x plus 4. And you might want to check that to make sure that it does distribute to be the trinomial we started with. Next, we're going to practice finding the GCF. So in part A, it seems like 7 is my greatest common factor. And we have 7n squared minus 21. So if we take a 7 out, we're factored completely there. You can't factor n squared minus 3 over integers. In part B, it looks like 9 would divide each term evenly, so that leaves us 9 times x squared plus x minus 2. Now, can you think of factors of 2 that add up to be positive 1? Well, if we had a positive 2 and a negative 1, those would give us 1x in the middle, and a positive 2 times a negative 1 would also give us that constant of negative 2 on the end. So our distributive property would look like 9 times x plus 2 as one binomial and x minus 1 as the other binomial. Part C, 4, 8, and 12 are all evenly divisible by 4. So if we pull a 4 out, 4x times x squared plus 2 times x plus 3. Will factors of 3 add up to 2? And that answer would be no, since the 2 is positive. And then finally on part D, it looks like 9 would be our GCF with 2y squared plus y minus 3. And here, I'm going to jump to the box method. I prefer this. If we have 2y times y, if you consider this is the 2y squared here. And next, we're going to think about factors of 3. So 3 times 1, 3 times 1, and I'm going to get my highlighter out. This 3 would give us a 3, but notice it's a negative 3. And we also want the middle term to be a positive 1. So thinking about this is 3 and this is 2. If we had 3y minus 2y, that would give us 1y in the middle. The only way to get negative 2y would make that a negative and this a positive. So using that box approach, if you're familiar with that, our binomials would be 2y plus 3, that's this row, times y minus 1. That's this row. So just a little organized method for keeping us straight with the multiplication and using that as a tool. Let's look at factoring when we have a leading coefficient that's not 1, similar to the example 2D. So you can apply this approach if you think about moving the 4 to the end. So I'm going to show you several different ways. If we put the 4 to the end, we have x squared plus 7x plus 3 times 4, that's 12. So I want to find factors of 12 that add up to 7. So if you use the box approach, x times x is x squared, and 4 times 3 is 12, and 4 plus 3 makes 7 when you do the outside and inside. So we have what we need, which is the row x plus 4 and x plus 3. But here's the problem. When I multiplied by 4, I've got to undo that to put it back the other way, so I've got to divide by 4. So that's called x plus 1. And then the x plus 3/4, I'm going to reconsider this and rewrite that. Instead of x plus 3/4, I'm going to rewrite that as 4x plus 3. Because if you think about setting that equation equal to 0, 4x equals negative 3, and x is negative 3/4. This x would be negative 3/4 to make that 0. So with that kind of logic, we call this method slide, divide, and pop up. When I end up with a fraction, I'm going to pop up that x plus 3/4 and rewrite that as 4x plus 3. Okay, in this next case, we're going to use the what my students called was the Stretch Armstrong method. So I want to multiply the a term and the c term together, and then we'll regroup. So a times c is 12. That means we're going to rewrite the trinomial. Since a times c is 12, I want to have factors that multiply to give us negative 12, but they also have to add up to our b value, which is negative 7. That would be this set of numbers, negative 3 and negative 4. So we're going to rewrite the middle term as negative 4x minus 3x plus 6. Next thing we want to do is we want to be able to factor by grouping. So let's just group the first two. That's taking out a 2x from the first term and the second term. It leaves us x minus 2. And if this method works, we need another x minus 2. So out of the second set of terms, what term is our GCF there? That leaves x minus 2. That would be negative 3. And then regrouping, we see that we have 2x and negative 3. Those are the two terms that get multiplied by x minus 2. You have to have 2x times x minus 2 and negative 3 times x minus 2 to use the distributive property twice. And like I said, my students used to call that the Stretch Armstrong method. That was a funny little toy that you could take apart. He stretched, and it had gushy stuff on the inside. So if you like that method, you can try this again. Excuse me. 3 times 4 is 12. I want to have factors of 12 that would add up to be negative 8. So how about if we did negative 6 times negative 2? That would multiply to be 12. And negative 6 minus 2 would add up to be negative 8. So regrouping, we're going to rewrite the 8x as negative 6x and negative 2x, and then the plus 4. So factoring 2 at a time, that's going to give us 3x. And over here, we would take out a 2, and the factor remaining would be x minus 2, and this factor remaining would also be x minus 2. So distributive property twice would be one binomial 3x minus 2 times the other binomial x minus 2. Now, here's where you want to be able to see a perfect square trinomial. So the key to this is recognizing that the middle term is double the a times the b. So when you see that pattern happen, then you can write a plus b quantity squared. And when you see that happening with a negative 2, a negative in the middle, that's the difference, a minus b quantity squared. So let's check that out in this example 4. Do you notice that 25 is 5x times 5x, and 4 is 2 times 2. And if you multiply 5x times 2, you get 10x, and 10x is double with the 20 in the middle here. So that proves to be a perfect square trinomial. When you see that pattern, you know that you have 5x minus 2 times 5x minus 2. That's where the 10x and 10x came from. So to rewrite that in the simplest form, that would be the binomial 5x minus 2 quantity squared. Do we have that same situation in part B and part C? I believe so. 64x squared is 8x times 8x, and 1 times 1 is 1 squared, and 8x and 8x add up to 16x. My x is missing there. So we have 8x minus 1 times 8x minus 1, or when you see that pattern, you know you have a perfect square trinomial, and that factors as the binomial squared. So looking at the vocabulary, this is a binomial squared. This is a perfect square trinomial. Same thing here. Binomial squared multiplies to be a perfect square trinomial. And then lastly, in part C, we have 4x squared plus 28x plus 49. So 4x times 4x, or I'm sorry, 2x times 2x is 4x squared. And 7 times 7 is 49. And then 14x doubled in the middle is definitely what we have. So 2x plus 7 times 2x plus 7 is the factored form, but simplified and factored completely is the binomial square 2x plus 7 quantity squared. So those are called factoring perfect square trinomials. Then the difference of two squares is what I call conjugate pairs, a plus b times a minus b. When you distribute a times b and b times a, those have opposite signs, so they're additive inverses, and they add up to 0. Now, don't be fooled by a squared plus b squared. This is the sum of two squares, and the sum of two squares, like part D, is prime. It cannot be factored. You can take out 9 here. 9 times 4 is 36, and 9 times 1 is 9, but it cannot be factored as the difference of two squares. The sum of two squares is prime. But part A is 4x plus 9 and 4x minus 9. Notice there's no middle term. Part B is 5x plus 6 and 5x minus 6. And part C is 3, now this one's tricky, 3m squared plus 1 and 3m squared minus 1. That's called the difference of two squares. And then lastly, for part 6, we're going to mix and match them all. Part A looks to me to be just like a GCF question. So I think we have, 4x would factor from each term. So 4x times xy would be, no, actually every term has a y, so back that thinking up. We have a 4x and a y. So 4x squared y, we would need an x, and 4 times negative 5 and one more y would give us negative 20 xy squared. And then in the last term, we only need a 3 for the 12xy. Part B, each term has an m in common. M squared minus 9m minus 10 is our first step. And I think factors of 10, we could use 10 times 1. And if negative 10 plus 1 was used, that would give us the negative 9 in the middle. So we want m minus 10 times an m plus a 1 to factor that completely. And then 2x squared, if we use the a times c method, 2 times 5 is 10. 2 times 5 is 10. I need factors of 10 that add up to 11. Can we do that? Well, we can't get a negative 10 and also add up to be a positive 11. So this is going to be prime. That won't work. This one is prime, because 5 times 2 would be negative 10, and I can't get that to add up to a positive 11. And then part D, we can take a 2 out of both terms. So 2x to the 4th minus 16y to the 2nd. And I see x to the 4th is a perfect square, and 16y squared is a perfect square. So we can use the difference of two squares as x squared plus 4y, and then an x squared minus a 4y. And I believe that brings us to the end of factoring and a review from Algebra 1.